Good morning, good afternoon, or good evening, depending on the time that you decided to watch our first video into our pre-calculus journey. Um, in this video, I'm going to spend a little bit more time than I probably normally would talking through some of the workflows and expectations associated with working on our Desmos activities. So if you have any questions, feel free to bring them up during our class time tomorrow. So every pre-calculus activity will begin with this screen that you see here. So we have our learning objective and we have a vocabulary for this particular lesson. Okay, the vocabulary you are tasked with defining. And yes, I am aware that you can simply Google these words and copy and paste the definitions, which is fine. Okay? If fine means merely going through the motions. Okay? I strongly encourage you to make sure that as you go and define these vocab words, you are critically reading what they mean and try to embed them in your long-term memory. It will simply just serve you better as we make our way through this course. Our learning objective for today's content is we are learning to comprehend why the properties of exponents hold for positive integers so I can generalize from repeated reasoning how exponent properties help us extend the definition of exponents from positive integers to all integers. I'll know I've got it when I can evaluate expressions with integer and rational exponents. Sorry, I'm dual wielding on two laptops, so trying to make sure I got both my screens ready to rock and roll. Here we go. Okay, so in this instance, we have a little bit of vocabulary. Okay? And you can also use the vocab here to kind of create your definitions. But if a is any real number and n is a positive integer, a little space there, then the nth power, so let me delete this, nth power is e to the n equals a times a times a times a times dot 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 times a. The number a is called the base, and n is called the exponent. If a does not equal 0, n is any real number, and n is a positive integer, then a to the 0 is equivalent to, use the math type button here so it kind of all looks good, to 1, and a to the negative n, if you've forgotten, is really rational expression. Okay? In this moment, you'd press submit, and the reason why I have our activities built in this way is you are now creating your own digital Juba book where 3 months from now, 4 months from now, maybe next year, school year, when you're taking calculus, whatever the case may be, you can now go back right after you press submit, and you'll be able to access this content as you had typed it. So I strongly encourage you to make sure that you are completing these to a relatively high degree. Okay, for this screen here, okay, you're presented with an algebraic expression, and I'd like for you to show me what you possibly remember. Okay, I'll start with the first one. Actually, I'll do the second one because I prefer the rationals. A to the m divided by a to the n. We can see that we have identical bases here, which allow me to subtract. There. I need a parenthesis. B minus n. There we go. M right from B. A to the m minus n. Okay, so when we have a rational expression that has exponent values in the same base, I can just subtract those exponent values while maintaining the value of the base. And I can obviously create an example, so I can do 3 to the 5th divided by 3 to the 2nd and demonstrate my entire workflows here, which is going to equal 3 to the 3rd power, which is really equal to 27. Okay, so you're tasked with simplifying all these expressions and making them together and putting them together. So I'm pretty interested to see how you guys handle the ones towards the bottom as they maintain a higher level of difficulty. Okay, and then obviously I'm tasking you to evaluate these numerical expressions. Well, once again, I'm aware calculators exist. I'm aware of things like photomath. And listen, if you're going to use them, there's nothing that I can do to feasibly stop you. However, I will be honest and forthright and say that you are probably lowering your own capacity to achieve. Um, to perform, to succeed. So I strongly encourage you to relinquish that reliance on um, alternative technologies and rely on yourself. Um, so go through, simplify the expressions you have here on the left, on the right, and we'll get into our next topic, which can get a little bit um, wonky, scientific notation. So within scientific notation, scientists use exponential notation as a compact way of writing very large numbers, very small numbers. Positive number x is said to be written in scientific notation if it is expressed as x equals a times 10 to the n, where our integers, or a is any value between 1 and 10, and n is an integer. Once again, make sure you press submit. So while I know it might have been some time since you've done scientific notation, let's spend a moment here refreshing that memory. So let's take this first number here, 1,000, not 1,000, wow, 1,750,000, right? So if we go back to our last slide, and I will see if I can, go arrow. Okay, we need to write it in a way that term being multiplied by 10 to the n is a numerical value between 1 and 10. So in other words, we are taking our decimal value, which is currently located here, okay, and we're wondering what numerical value times 10 to what exponent power will correlate. With place value, as we move our decimal value to the left, we are simulating a multiply by 10 effect. Hence why we have the ones and the tens. 1 times 10 is 10, and 10 times 10 gets you hundreds, and hundreds times 10 gets you 1,000. So we've done this 1, 2, 3, 4, 5, 6 times. Right, so we have 10 to the 6th, and if our decimal point is here, oops, we have 1 point, come on, 7, 5 times 10 to the 6th. And to verify, we come to our table, we can type this in, and it won't appear here because it becomes a very large number, but you could use a decimal calculator and things of that nature. Okay, I want to see how much of this you remember, since this technically is an Algebra 2 rewind, and we have both positive and negative exponents. So please input your answers here. If this is a little confusing or frustrating, please be sure to note it and bring this to the discussion during our debrief in class. Okay. Radicals. Okay. This symbol here, we should be well aware, is our radical. We could say radical slash square root. Okay. If n is any positive integer, then the principal nth root of a is defined as follows. Right? This expression, let me delete that blue. The nth root of a is equal to b, which means, get my math type button, b to the n equal to a. We can talk about this process here in class, but I'm going to go out on a limb here and assume that you've known how I've algebraically manipulated this statement, which led me to this statement. And don't forget, because of domain, that if n is even, meaning we have a square root, a fourth root, a sixth root, whatever root, that a must be greater than or equal to 0, right? We cannot have a negative value underneath the square root or even root symbol, and that simultaneously b would have to be, well, greater than 0 as a result. Okay. Once again, we get to this properties of nth roots screen. I'm going to go through the properties with you and ask that you provide me with some numerical examples. So here we have the nth root of a times b, and we can separate, because of our multiplication properties, this radical expression where we tease apart the factors. And the same would hold true in the event of division, assuming that the can't remember the does not equal sign. Let's see if it pops up on the keyboard. Does not equal ABC functions. I guess not. But so I won't type it here. But assuming that b does not equal 0, right? Because we cannot have a divide by 0 situation. Okay. In this case of the indices, right, we have the nth root of the mth root of a. It's a mouthful. You can take those two indexes and multiply them together, have one final index. Okay, and in this case, right, when we have the nth root of a to the n, if n is odd, so we're talking about the cube root, the fifth root, the seventh root, our value here would simply be a. If you have a to the fifth, you want the fifth root of that, right? If you think about exponentials and radical functions, they're inverse operations. However, when n is even, i.e. squared, fourth, sixth, eighth, we must take into consideration that we will arrive at two values, the absolute value, and when you go to create your numerical example, that should kind of solidify this journey here. Once again, if it's something that is a little confusing, let's bring it up in class together, where we can have a discussion about it. Brings us to our final topic for today's content, or I think second to final topic, actually, excuse me. For any rational exponent, m divided by n in lowest terms, where m and n are integers, and n is greater than 0, because if it's 0, it's no bueno. We define a to the m over n as nth root a to the m. Right, so the numerator represents the exponent of our base value, and the denominator represents the index of our radical function. I think I wrote the same thing twice. Oh, I see what we can do. Apologies. A to the m. So technical difficulties, my apologies. There we go. You can also take this base of the base, and we can erase it after we apply the radical. Is there necessarily one better representation over the other? No. What it really boils down to is context. Sometimes it's better to kind of use this notation, sometimes it's better to use this notation, but once again, it really boils down to your ability to kind of work intuitively with these numbers. And last and most certainly not least, if n is even, right? So thinking back to the even roots, we require that our value inside the radicand is positive. If it's not, that's going to be a problem. Okay, so in checkpoint 3, once again, you'll make your way through these, okay, converting from radical form to non-radical form, and in this instance, applying some exponent laws. But let's see what you come up with, and we'll have a conversation with it if anything looks awry. So finally, we've arrived at a topic where I can elicit some of your knowledge and insight. Maybe you've never rationalized a denominator before, maybe you have, but describe a strategy for rationalizing a denominator. So what is a rationalizing a denominator? It's a procedure in which we eliminate the radical in a denominator by multiplying both numerator and denominator by an appropriate expression. A fractional expression whose denominator contains no radicals is said to be in the form standard. Which brings us here. So this is a process that we're going to work out together. So going back to the previous page, once again, rationalizing the denominator is a procedure in which we eliminate the radical in a denominator by multiplying both the numerator and denominator by an appropriate expression. So in this instance, we have my pen tool. We have x over the square root of 3y. Now, in order to eliminate a radical, we'd have to go back to kind of those radical properties. Case in point, if we have something like the square root of 3 times the square root of 3, this will yield the square root of 9, which will give us a whole number. So part of my multiplication will be a square root of 3. However, there's also an additional factor, so I want to include that as well. However, remember, we need to multiply by both that term in the numerator and the denominator. And the reason why we do that is because if you think about it, this expression here, if we were to simplify it, it really is nothing more there we go. Nothing more than an algebraic 1. So yes, while we're going to modify our original expression, we're not actually changing the structure, the origin of this particular number. So our numerator would become x times the square root of 3y, while our denominator is the square root of 3y times the square root of 3y, which would give us the square root of 9y squared. And if you remember your properties of exponents, the square root of 9 is really a 3, and the square root of y squared is really y. Now you might be sitting there and saying, well, mister, look at you writing on your computer. Okay. Fear not, you will become much better at this over time, but I would like for you to embrace the challenge, as this would be good practice for your future careers in STEM. That's the route you decide to pursue, where you can type your entire expression, 9y squared, and properly demonstrate your entire solution path. And for the purposes of this course, our assessments will be on here. However, you'll be able to share your answer with the class so everyone can see your solution strategy and kind of work collaboratively while attempting to solve this on your own time. And that brings us to the final installment of our first activity. At this point, you should be able to go no further, and we will pick up with our enhancement opportunities together in class. You'll have an opportunity to work through some of the practice problems, utilizing both me and the strengths of your peers. If you have any questions, make sure you write them down and you bring them to tomorrow's debrief.